So this is just continuing the discussion about the shortcut formula for the sample standard deviation. In the previous video, we got this definition formula, and then we stated this shortcut formula. I showed you how to do the algebra to get from here to here, but I did it with the population standard deviation instead because it comes out a little nicer. But anyhow, this formula for S and that formula for S are algebraically equivalent. They produce the same results. So this one is going to be easier to use, and I want to demonstrate how to use it with the data that we have about the diameter of the oak trees. So we had 27 randomly selected oak trees. We've measured their diameters, and that's in this column. And then the squares of all those numbers are over here in this column. So we have all the x's, the xi's here, and the xi squareds here. And down at the bottom of the table, I've added them up for you. You see how you can do the sum in Excel. I did the sum of all these xi's. And then here in the adjacent cell, I've done the sums of the squares of all the xi's. And so at that point, once you have these two numbers, it's easy to use the shortcut formula. There's not a lot of work left. Let me go over there to the document camera and fill that in. So I'm going to copy the formula. All right, the big square root in here is the sample size. There were 27 oak trees. So I have 27. And then the sum of the squares of the x's. That's the 726.68. And then we have the sum of the x's in parentheses squared. The sum of the x's from the data over here is 127.6. We divide by n times n minus 1. N is the sample size. There were 27 oak trees. So that's all there is to it. But now I want to show you how to do that shortcut calculation in Excel. So what I'm going to do is make this window a little bigger. Okay, so overall, you know what? Let me break this up into pieces. Let me just do just the numerator, just the top of the fraction inside here. Okay. So let's see. I want to do my 27 times 726.68. I just click on the numbers. I'm less likely to make mistakes if I click instead of type. So I do the 27 times 726.68 and then subtract this thing squared. I don't really need the parenthesis, but here. Oops. Okay, there. So that's the numerator. And I want you to notice something. See, if I was doing it totally by hand, I would have rounded out. This 726.68 has been rounded off. Well, I guess that's all the digits there are, but if you do this clicking thing that I'm doing, if there were any extra digits in there, they would be kept, and you want to keep all the extra digits in all your intermediate steps. You just round things off at the very end of the calculation. Okay, so there's the numerator. And then the denominator, so that's the 27 times the 26. So I'll take this guy times himself minus 1, n times n minus 1. So I get that. And then when I divide to get the quotient, taking that numerator divided by the denominator, and there I get all those extra digits, which is just fine. And now I'm ready for the final answer. I do the square root. And these diameters were in inches. So, so this quotient here was, this was squared inches. All right. The numerator was squared inches. The quotient was squared inches. And then when you take the square root, it's back to just plain inches. And we have a rule about the accuracy of the sample statistics. You keep one more digit than the original data had. That's true for the mean and the median and the quartiles and the standard deviation. So the interquartile range as well. So I want, see, the original data was accurate to the nearest 1/10 of an inch. So my sample statistic is going to be reported to the nearest 100th of an inch. Oops. Get that out where I can see where I'm going. Okay. There we go. So because the original measurements, we didn't really know what came out, after this 5.8 inches for tree number 17, we don't really know what came next. It might have really been 5.81 or something. So that limits how much accuracy you should report. There's a standard to allow the one more digit, because if you want to do like the average of 5 and 6, you need, 6.5. You need the one more digit to indicate you're going in between. But it's sort of understood that then the original data was not showing that extra go-between digit. So anyway, here's the final result. Now, Excel can also do all this more quickly. You don't always have Excel, so I want you to see how to do it, just with arithmetic. But doing this with Excel, here's what happens. I just select the data and close the parentheses, and it gets me the same thing. Okay, so that's all for this presentation.